Hello students, in this video of chapter Chemical Kinetics, I will be talking about collision theory of bimolecular reactions. Let's start. Any chemical reaction used to take place when there would be a collision in between the reactant molecules. It may be expected that rate of reaction is always equal to the rate of collision. For gaseous phase, we know that gas molecules used to colloid with each other, and the collision is far more and typically many powers of 10 compared to the observed state. For the reaction occurring, the colloiding reacting molecules must possess some kinetic energy, and this minimum kinetic energy is the activation energy. The reaction would occur only if the colloidal molecules will possess kinetic energy equal to or greater than the activation energy. And when the molecules are colliding with each other, that means they have a successful collision with each other is sufficient for the reaction involving the simple molecules, but not for the complex molecules. Beside the collisions, the molecules should have the proper orientation. The molecules need to be oriented relative to each other so that the reactants would convert it into the products. Let's consider the example. For example, I have two reactants A and BC, and where what is going to happen, the product will be forming AB and C is going to be isolated. Here in this reaction, C and B are bonded, which is need to be broken by the collision, and the new bond formation has to be taken place in between A and B. The collision of A with C approaching toward A would not lead to reaction if the reactants are colloiding and they are not exceeding the activation energy. Plus, if they are not in a proper orientation, the reaction would be successful when both the molecules are properly oriented and the activation energy they are crossing. Now let's talk about the potential energy barrier. During a course of collision, new bond in between A and B will develop. At the same time, the bond between B and C will break. The configuration in which all three atoms are weakly connected to each other, that configuration is called as activated complex. To attain the configuration ABC, which is the activated complex, need to gain energy which comes from the kinetic energy of the colloiding molecules. The energy barrier between the reactant and product is shown in the diagram. You are seeing potential energy barrier. The reactant molecule need to climb up and overcome before they convert into the products. The height of this barrier is called as activation energy or EA. Thus, the reactant molecule transform into the product only if they possess energy equal to or greater than this activation energy. And one more thing I wanted to tell you here is a fraction of molecule those possess energy greater than activation energy is equal to F is equal to E raised to power minus EA upon RT. EA is activation energy, F is the frequency, R is the gas constant, and T is the temperature. Because of the few collision and the proper orientation, what is happening? The products would be forming. Now we will be talking about the temperature dependence on the reaction. The concentration change only a little with temperature. The rate constant shows a strong dependence on the temperature. For that, we are going to learn Arrhenius equation. Arrhenius suggested the rate of reaction varies with temperature and the relation is K is equal to A e raised to power minus A upon RT. K is rate constant, E is activation energy, R is molar gas constant, T is temperature in Kelvin, and A is pre-exponential factor. This equation is also called Arrhenius equation. The pre-exponential factor A and the rate constant have same unit in the case of first order reaction. Besides, A is found to be related to the frequency of collision. Now, let's see the graphical determination of activation energy. If from Arrhenius equation I am obtaining the equation ln K is equal to minus A upon RT plus ln A. On taking log base 10, what will happen? Log base 10 K is equal to minus EA upon 2.303 RT plus log base 10 A. If I am comparing this equation with the equation y equals to mx plus c, I will get to see the graph plotted in between the log base 10k and 1 upon t is a straight line. The slope of this line is minus EA upon 2.303 R with its intercept being log base 10 A. Now, determination of activation energy for two different temperatures. Let's suppose these two different temperatures are T1 and T2. For T1 and T2, we will be having different K1 and K2. For respective K1 and K2, we are writing Arrhenius equation, and if we are finding out log K2 upon K1 is equal to EA upon 2.303 R in bracket 1 upon T1 minus 1 upon T2, when the two temperatures are given with two rate constant for a reaction. Now, the graphical description of the temperature. It has been realized that average kinetic energy of molecule is proportional to temperature. That means bimolecular theory is saying that if the reactant molecule have sufficient kinetic energy and proper orientation, then only they will be converting into the products. At a given temperature, the fraction of molecules with kinetic energy equal to or greater than EA or activation energy, then what will happen? The product will form. When we are increasing the temperature, fraction of molecules having activation energy, it will increase. The rate of reaction will also increase. This was showing us that by plotting the fraction of molecule with a given kinetic energy versus kinetic energy of two different temperatures, that is T1 and T2, the shaded area is proportional to the number of molecules. The total area is same at T1 and T2, and the area A plus B, you would say, represents a fraction of molecule with kinetic energy exceeding activation energy is larger at T2 and it is lower at T1. It is showing that a fraction of molecule possessing larger energy than activation energy, and this larger energy is due to the increase of temperature. So, the rate of reaction is also increased. So, this is all about. Thank you.